Welcome back, students. In this video, we're going to look at the complete Sn2 mechanism. Let's start by reminding ourselves what the Sn2 mechanism looks like. In your Sn2 mechanism, there are two steps that happen at the same time. The nucleophile attacks and pushes out the leaving group, so the leaving group leaves. These two steps are combined, which means that this is a concerted reaction. In this concerted reaction, if you were to have a chiral center at the beginning, you would see inversion of configuration at the end. In addition to this main combined step, you can have a proton transfer that happens before the combined main step, or you can have a proton transfer that happens after the combined main step. Let's look at an example of each of these. If you start with an alcohol where your OH is meant to be your leaving group, you need to protonate that OH first. OH on its own is a terrible leaving group. What we'll do is we'll add some acid in order for us to protonate that OH and turn it into what I call bound water. Let's draw that out really quick. I'm going to add my electrons onto my oxygen, and I'm going to redraw my HBr so that I have a bond between the hydrogen and the bromine that's visible, so I can show that bond breaking. The electrons on the oxygen of your alcohol are going to come over and they're going to pull off a proton from your HBr, and then this bond between H and Br needs to break because hydrogen can only form one bond. Then when we draw the subsequent step, we now have a hydrogen attached to this oxygen that wasn't there previously. This makes the oxygen positive, and it looks a lot like water. Like I said in an earlier video, this bound water has a fancy chemistry name, but do we really need to memorize another fancy chemistry name? Probably not. So I'm going to call it bound water so that you can identify it more thoroughly. What happens now is your nucleophile can attack. You might be stopping and thinking, where is my nucleophile? Well, you just got rid of bromine, and now you have bromide ion. And bromide ion can behave as a nucleophile. What will occur is the electrons from bromine, and would choose whatever pair you want. You'll start your arrow at a pair of electrons from the bromide ion. You'll point to the carbon that has the leaving group attached, and then this bond needs to break and the electrons will go on to your leaving group of oxygen of the bound water. Now what happens is we have our bromine attached and we have some H2O floating around. So just remember that OH on its own is just a horrible leaving group. This is one way that we see an additional step be added to the combined steps in the Sn2 mechanisms. We can also have a proton transfer happen after the combined step. I want to show you an example here. I have my H2S, which is going to be my nucleophile. You don't know yet that DMSO is a solvent. We're going to look at that in the next video. The H2S is going to be my nucleophile. Here is my bromine that's pulling electron density its direction. So the carbon that bears the partial positive charge is going to be your electrophile. And if you're a super duper organic chemistry student, you might be looking up your electronegativity values right now and recognizing that bromine's not that electronegative. But in organic chemistry, we usually just assume that all of the halogens have enough electronegativity for the carbon that they're connected to make that carbon partially positive. We will then start our arrow at a pair of electrons on the sulfur. It will attack the carbon of the electrophile and force out the leaving group. When this happens, now my sulfur is going to be attached. So my sulfur is going to be attached where that bromine was. Nothing happened to the two hydrogens that were already on that sulfur, but that sulfur is going to have a positive charge now. Now that I look at this, I see that my sulfur has that positive charge, and usually you don't want positive products, so something needs to come in and pull off a proton. When something comes in and pulls off a proton, there can be a couple of ways to write this. If you are not given a subsequent base, then what you need to do is you need to look at the bromide ion and you need to look at H2S and decide which one is going to be the better base. In this particular example, I looked up the pKa of HBr and of H3S+, and they're pretty similar to one another. They're both around negative like 4.5-ish. So I would say that the best way to carry out this reaction would actually be to add another different thing that's actually a base, but sometimes that doesn't actually happen on paper, because if we add too many things, then students get confused. So what you could do if your teacher doesn't add another thing is just to utilize one of the components to pull off that additional hydrogen. And it's going to be whichever one is the stronger base. I'm going to use H2S because I just want you to recognize that reforming hydrogen bromide is something that isn't going to happen in other reactions, and that's why I don't want to show it to you here. And now we get our product. This is going to happen when your nucleophiles are neutral. When your nucleophiles are neutral, you're going to end up with a positive compound after you add that nucleophile, and so that's why we need a proton transfer at the end. Let's wrap up. Sn2 reactions are a little less complicated than Sn1. You have a concerted process where you have a loss of leaving a group happening at the same time that the nucleophile is attacking, and you only have two potential additional steps, a proton transfer at the beginning or a proton transfer at the end. Notice there is no possibility for a carbocation rearrangement, which we saw in Sn1 reactions, because there's no carbocation formed. So how could it rearrange if it doesn't happen? It can't. So it's just the Sn1 reaction that is going to be able to do that, not the Sn2. Thanks so much for your attention. This is Katoni signing out.